So next speaker is Mikhail Gromov. So Misha is known for his fundamental contribution to many areas of geometry. So let's just mention symplectic geometry, hyperbolic geometry, geometric group theory, and many others. So in relation to this conference, just let me mention that I think probably one of the first papers by Perelman, maybe really the first paper was a joint paper with Gromov and Boraga. Also, let me mention another fact. So it's yesterday, Bill Thurston mentioned that it's after some point he was 99% plus sure that Poincare conjecture is true. But on the other hand, as recent as 2002, I think there was a conference somewhere, and there was a conversation, and Misha mentioned that from a certain point of view, the probability that Poincare conjecture is true is close to 0. So it's
yeah. So actually, I explain. I think it's still close to 0, right? But that's, I think, is right. The point about mathematics in general is completely the kind of least logical of all sciences. Everything what we prove, worth proving, is just shouldn't be true, right? Otherwise, so about that, you know, this painting, yeah, and that's because I cannot make such beautiful painting as other people, so I borrow them from the net, and you know, this is a question usually people ask about ourselves. We ask but this essentially the last question. It's better not to know the answer. Yeah? But for manifolds, we may ask it. And now I want briefly to show what I'll be talking about, so you can read it. So you have some ideas, and maybe you start asking me questions, because there is kind of it's not systematic talk. There are kind of glimpses on different subjects, which I want to make. And essentially, what I want to do is just change the perspective, because it's a big event, and just we want to look in the large time scale. And what is the largest time scale we can look at topology, right? What do you think, how far we can go? Is still see something of topology, and how many years? What do you guess? You go in time, and still we see topology. And actually, we shall see what Bill essentially, something very similar to what Bill was demonstrating during his lecture. How far can we go? 30 million years. We can go 30 million years sideways, not backwards, not in the future, but sideways. How can we go 30 million years sideways? So let me show you. Here. Here is our relative, and it is orangutan. And unlike chimpanzee, he is really very far from us, right? It's removed by 15 years, well, roughly 15 million years of evolution. And certainly it's by the tree, it's 15 million years here and 15 million years there. So it makes 30 million years. And still we are now in time. And this is not this particular one, but the name of which I mentioned before. Yeah. Yeah. Yeah, I cannot see it. Kinyé, yeah, his name or something, yeah? I have to go before. Yeah. His fellow was recorded doing exactly the same what Bill was doing. You know that? So what he was doing, whenever he was given a piece of a house, he would make a circle, right? It would go through it back like that. Yeah. And I think it's not just funny. It tells you something quite remarkable. So there are two things which are kind of anti-scientific, but kind of very mathematical. First, it happens very rarely, right? You don't see many people doing what Bill was doing. Yeah? It's rather exceptional. And also for this particular individual, it was exceptional. No one of these other apes was doing that. Secondly, from the point of view of external observer, it's a completely meaningless behavior, right? Right? And actually, there's also psychologists who is observing that, but they're saying it's kind of strange. It doesn't fit in the idea of intelligence. Yeah, they thought it was not very intelligent. But on the other hand, so it cannot be accidental. It's very complicated behavior, right? And it came from very different sources. Therefore, it must be modulated by something universal. So it means topology is universal, and the way we generate it universal. And that's, I think, is fantastic proof, exactly because it's so rare. If it were a common thing, you would say some trivial explanation. Because it's so rare, on the other hand, potentiality of this happening, even probability much smaller, it means there is something kind of fundamental behind it. So I want to say this kind of fellow justifies our interest in topology. It gives you external view, and it's still exciting and interesting, not only for us. Right? And that's a good sign. Yeah? So we are not alone. So what come next? So have I shown you everything? Yeah? Right. So as you look at this, yeah, there are some people whose name mentioned there, they may be curious, of course, what I'm going to say about that. Yeah. So I'll come back and try to be quasi-systematic. So just one point, which is here I want to, because I will be not saying much about mathematics, I just brought here the conjecture by Whitney, because it was one of the indicators that something special was happening in small dimensions, especially dimension 4. So Perelman, of course, is just something about dimension 3, but it's kind of inseparable. Yeah, small dimensions are inseparable. And so the turn which was taken by topology was, yeah, because I wrote something, I just expect you to ask questions because I cannot see exactly what's written there. So, and kind of about many things. I don't know if I'm kind of will be saying there, but I just want to just one mathematical example. It's theorem of Whitney. It was conjecture by Whitney, and the interesting point, but because it's my personal perspective, my kind of first kind of turn I experienced when this something strange was happening to topology. Because when you're learning topology, under influence of Poincaré, there was this idea you forfeit, you forget everything geometric. You just live in this very rarefied atmosphere of topology, and it was believed, at least the way what I was learning from my professor Auckland, that all topology, at least in lower dimensions, was kind of there, except you have to combine it properly, and just algebraic topology and a little bit of geometry will tell you everything. But then there was this question raised by Whitney in 1940 about what possible kind of geometry of embedded surface in force space. An interesting point was when it was non-orientable surface, like projective plane inside of a force space. Like if you have a knot in the 3 spaces, it might be very complicated, but if you take small neighborhood of a knot and forget how it sits there, all neighborhoods are the same. It's just product of a circle by this normal section, and that's it. And the same would be true for orientable surface in force space. Yeah, it will be just, regardless of how it twisted outside, if you look only around it, they're all the same. But Whitney realized it's not so for non-orientable surfaces. However, he conjectured that the number of these local topologies or geometry is finite and gave specific estimate. And this was a conjecture, and nobody could solve it. And then it was solved just, I think, about 70 something, or like 60 by Massey, and it was using Archer-Singer theorem. And then it was kind of course, the theorem already was kind of there, and of course I couldn't appreciate kind of grandeur of that because I was learning it as I was kind of learning everything else. But for my professor Auckland, this was a really shock, yeah, that there was something coming from analysis and then proving something in the domain he was kind of an expert, that the topologist, and he worked in dimension 4, and would never come from anything else. Yeah, it was first indication that geometry could change the perspective in topology, at least in dimension 4. And now, of course, this theory of surfaces for manifolds was grandly developed within the Donaldson theory, but still, I understand for this particular even piece of that, there is no purely kind of traditional proof. Right? It's a very simple statement, I repeat. It's just how a surface, non-orientable surface, looks inside of a force space. And it's kind of looked extremely simple, naive question, kind of like exercise. It looked like exercise in algebraic topology. But it couldn't be solved without some geometric or analytic kind of point of view. So there were these turns, which I meant, these sharp turns, which topology undergone. First, it departed from geometry, and it was Poincaré actually was expressing this very powerful, very remarkable idea. You can go away from that. But then there was a kind of turn back, and this was kind of the last corner of this turn, this theorem by Perelman. Now I was saying something about what? Yeah, so geometry is back. Yeah, well. So just, yeah, you may ask me something, because I will not be saying about anything, but certainly if you have some particular question. Huh?
Who is naked?
Who is naked, yeah? Who is naked, yeah. So just when you, at least it was my experience, just accepting this kind of, coming from Poincaré point of view, that you have this naked, this topology naked of geometry, completely kind of bare, and it was really painful, and you always felt cheated, yeah? And then you learn it and accept it. And then, boom, and you have to go back, yeah? And certainly, so that power and this charm of this algebraic topology is unclear how real was that, yeah? Is it was really something fantastic, or it was just a way to bypass kind of the real issues, yeah? And it's still a question, I don't have an answer to this question. From point of view of this low dimensional development, well, that maybe it was just naked, yeah? We just don't have this dressing yet, this meat yet to come, or maybe not. At least we never know. I mean, well, eventually we may know, I'm sorry, but we don't know it now. So I don't know who is naked. Or of these people whom I kind of, who's there? Yeah. And then there was this kind of turn, is marked first by the work of Bill, and this was just, as I said, the first turn coming from Michael Singer, I couldn't properly appreciate it, yeah, because you just grow with this. But with both Thurston and Donaldson, they changed perspective in a very radical way. And so one concept coming from Bieland was completely kind of unacceptable at the time, that something so special as hyperbolic three manifolds may cover a domain of something so huge, all three manifolds. It was absolutely kind of counterintuitive. And on one hand, we kind of knew about both domains, well, not me, but some people knew about both domains, but they look completely kind of incomparable in size. And it's kind of one point. Another point is that majority of manifolds are hyperbolic. And then it dwarfed completely things like Poincaré conjecture. It was just one tiny little thing, and who cares about that, yeah? Right? Because and it was kind of shown, right, by you, that most manifolds are hyperbolic. And why to care about Poincaré conjecture? Right? Yeah. But it's another point is that instead of manipulating with manifolds, you have to manipulate with metrics on manifolds, right? And this was kind of, this idea is crucial, of course, for the following development. And another thing which was not often emphasized, that you say there are different classes of manifolds, but then how you glue them. And when you glue them, and it's kind of essential point, you think about now in geometric term rather than purely topological. So in dimension 2, of course, we have the circle. But in dimension 3, we have two kind of symmetric gluing, right? It may be either torus or a sphere. And certainly, when you geometrically glue, say, hyperbolic manifolds, this gluing pattern is symmetric. So and it's not canonical gluing. Topologically, it's unique. Geometrically, they come in families. And it's exactly those families which generate singularities in the flow of Hamilton-Perelman. And then there is chopping off, all implicit in this picture of three manifolds, right? And this is what I would call entropy for the following reason. So when you have mathematical difficulty, like in physics, has two components of this. It's entropy and energy. And energy, you kind of see what it is. When there is a difficult proof and you have to go uphill and you follow the author, it's very hard to go, and you know it's hard. Entropy is something invisible. You just have to decide where to go. You have many directions and you have to decide. And one decision is made and you have this picture, you never notice afterwards it was so difficult, right? But to find this out of the vastness of things one direction, incredibly difficult, yeah? It's as difficult as to go uphill, or it's another kind of difficulty. And this is often forgotten, this little thing, like this picture, which was not actually originally in Hamilton presentation. When Hamilton started, he was speaking about flows in geometric context and equations, and then it looks completely absurd what he was saying, yeah, because from topological point of view, what he was saying was inconceivably impossible, and it's only was possible when it incorporated this idea coming from the hyperbolic geometry of Thurston. It was one thing. And Donaldson also, of course, he proved difficult, like Thurston, kind of high energy theorems, but there was a concept which is inconceivable before he entered, because never before nonlinear differential equations were saying something in topology. Just never. It just never happened. And so you could believe it is impossible, right? And it was the first instance of that. And the fact it was possible, it was kind of crucial. And so these three components going into Perelman, and one from Thurston, Donaldson, and from Hamilton, of completely different nature. Because here and here, we had instances of geometry truly interacting with geometry. Topology and geometry were talking to each other in a fantastic new way. In Hamilton, it was pure geometry analysis. There was no single indication that his method can give anything topological. Because you see, differential equations, the classically, as people do them, they have kind of equation, and so they say coefficient, and say they're in this interval, and have these absurd things. And somewhere, I think you Michael, may notice that the point is to have equation in the maximum generality. And if you can extend them to their domain, and they become topological, and then the real power and beauty of them is shown, right? This is kind of, you said it in different words. But that's a crucial point. The equation become kind of powerful, remarkable, real part of the mathematics as we geometers understand it if they go to the real domain of existence. And if they reach this boundary, and then this boundary, grand things happen. And this was not in Hamilton theory. And therefore, as I was saying, I didn't believe ever in that. And I never spoke to Perelman, yeah, because I had such occasion. Once I spoke to one of my friend, Eli Asberg, explaining him why his method to proving that foliation exists cannot work. And then Bill proved it, yeah? And I had very good argument saying there's such no chance like that. and so is here. So, and yeah, that's a little bit about this perspective. And so what comes next? Right. Now about these numbers, yeah? I think I promised to say what's special about these numbers. Because this was mentioned several times, there was some geometric explanation, but I think there is a more fundamental one, and which I already I keep repeating for quite a while, and this is the same reason why these numbers are special in solving algebraic equations. But now just imagine we turn, kind of distort the history, and suppose that first people just develop high-dimensional, high-degree theory of equation, with a ground theory, and then they say there is no solutions. And that's like high-dimensional Poincare conjecture. There is no solution except for trivial one. And then, after certain work, they found this formula. This is a fragment of this formula. And now they may not look so exciting, but if you think about this incredible formula, you have a simple equation, and then boom, this huge formula. And then they would say, well, that's the end of the epoch, and so everything is finished, and there would be no Galois theory, no class field theory, no Linglen's program, no Wild theorem, nothing. We stop. That's a rather strange attitude, right? But they didn't think in these terms. However, the point was that they didn't try to repeat this, what was in dimension 4, right? They didn't try to find this formula. It was something completely, even more beautiful, but equally structured, yeah? Not kind of statement something doesn't exist. And that's the point. This, I think, in topology, we have to look for something comparably interesting. And now, why truly these numbers are equal? Why so special about this number? Why this? It is not quite metaphoric, but true. And that for the following reason, yeah? There is something very special about this identity, 4 equal 2 plus 2. And it's very different from any other identity for the following reason. 4 equal 2 plus 2 in 3 different ways. Because you can decompose 4-element sets, right, in two halves in 3 ways. If you take any other number bigger than 4, right, for small, forget about it, you have much more. Right? If you decompose 5 and 2 plus 3, it's much more, etc. There is no other configuration like that. So what it means, yeah, it means if you have 4-element set, you can out of that canonically to have 3-element set. It means that permutation group on 4 points admits a homomorphism to the 1 and 3 points. The group is not simple. So the group of permutation for elements is not simple. And this, of course, most dramatic seen in the Young-Mills theory, because it implies that the Lie algebra SO4 is not simple. So it splits in two. So the trivial kind of equation, minimizing something like integral curvature, splits, and we have equation of the first order. And then you have index theory, and then you have Donaldson theory. So you can say that this is kind of the proof of the Donaldson theorem, right? This is the kind of specificity of the problem. Everything else is huge kind of theory, but it's universal, nothing special. About 3 is not so clear, because 3, it's kind of simple group. Of course, it's a abelian simple group. And indeed, in the dimension 3, we don't have kind of such a structural clarity. Which even in dimension 4, we don't have it, but in 3, we have less, right? And so, coming back to geometry, why dimension 3 is that special from this point of view? In dimension 4, it's clear. However, this identity tells you that these numbers are kind of related in an intimate way. And if we use this kind of 2,000 years ago, maybe we knew many other things, but today. So, what happens to my glasses? Now,
2 equals 2 plus 1 and 3, right? 3 equals 2 plus 1 and 3, right?
In 3, but 3 equals to 3, you see? You don't have no reduction. It's not less. 3 is not smaller than 3. Right? So you don't have a homomorphism of groups, right? It's still the alternating group and 3 elements. Huh?
The sign.
Yeah, no, but alternating group, yeah. Of course, people about alternating group is still simple for 3, right? The only case where it's not simple is 4. The alternating group is not simple. And of course, it's abelian, and that, of course, corresponds to the abelian class field theory. I mean, I think it's kind of very superficial what I'm saying. It may seem, but it may also indicate very deep undercurrents, yeah. But this identity, I think, is one of the most fundamental in mathematics. So, okay, now, I want to briefly indicate where manifolds come from, and that we don't quite have full picture of that, yeah, because there are rather limited number of sources when they come from. And say triangulation in surgeries. This is kind of going along to kind of combinatorial mechanism which can be shaped in algebraic topology. However, again, I want to emphasize a problem which come from mathematical physics, which is unsolved, which is indicating that we don't understand what triangulation is. And the problem is extremely simple. You take a manifold and just ask how many triangulation it has with a given number of simplices. So it's some number depending on this triangulation. So I have your manifold X, and have the number of triangulation with k simplices. Yeah? And you want to know what happens to it when k goes to infinity, roughly. That's how you take triangulation up to isomorphism. And there are immediately two alternatives you can see. It's bounded from below, but some constant, well, put it this way, 1 plus something, so it's epsilon to the power k. And it is bounded from above by k to the power k, roughly. That's kind of trivial. Just keep subdividing. You have this power, and if you see how many kind of automorphism you have on a k-element set, the question is, where the truth? Where between these numbers you are? And nothing is known. It's absolutely blank, right? For surfaces, you know, it's like that. And physics has kind of made this computation. But you can easily produce that. And the point is, and actually there is a manuscript in physics when they prove this bound. But as Steve mentioned, they exactly make the same mistake you do. They don't use the fact it's the fixed manifold, right? The whole point manifold must be fixed, right? If you vary the manifold, of course, here you can anything, you would have that. The question is if you fix manifold. And so the subtle point is fixed topologically. how this combinatorics of this triangulation tell you something about topology. We think we understand it, but when we look at this problem, we don't. We have triangulation here, abstractly topology there. We just know that it's the same, meaning homeomorphic, or diffeomorphic, homotopy equivalent, whichever. But we absolutely, there's no direct link between the two. And, well, so that's a big kind of, we have zero-level question in topology, right? If you start with triangulation, you cannot answer that. And there is something behind it which kind of some possibly related phenomenon, also explaining that given usual way you present a manifold, for example, by triangulation, and on the other hand, you speak about its topology, on one hand, triangulation determines everything. On the other hand, from dimension 4 on, I'm always confused 4 or 5, yeah? It tells you nothing. Because you know that if you have, you may have trivial fundamental group, and so your manifold may be topologically a ball or a sphere. However, this equality is just kind of philosophical, yeah? You know it is so, but you don't know in reality, because the group you have, the presentation of your group, is algorithmically not solvable. Which means in practice, in order to contract a loop, yeah, I mean just time of the universe will be peanuts to that, yeah, it will be just, for all practical purposes, it will be infinite time. So it's contractible in some philosophical sense. In reality, it's not. So we don't know, we cannot tell what is fundamental group of your manifold by looking at triangulation in a very deep way. I mean, just this, more than any infinity you can have an analysis. Yeah. So, and that it particularly shows that geometric approach, as we know it in low dimensions, in principle cannot. Well, I have to be careful, but it seems it cannot, in principle, work in higher dimensions. And this was always also possible objection to a method like Hamilton. Because in dimension 3, it seems it barely works. Yeah? In dimension 4, it just cannot work. If you start with something 4-dimensional, no geometric process will bring it to something canonical. Because always, on a very simple space, you can make this horrible twist, and the space will look very innocuous and nice. However, this twist is there, and just you see nothing. Yeah? You think you see it, you know nothing. That's one of the problems. And then, coming back to different presentation, right? So I wouldn't speak about Lie group in homogeneous space. Everybody knows that. That's the basic points, basic classes of examples. But I can say one word about kind of classical way to generate manifolds. Kind of, by now, the essential was brought in by Tom, right? So you start writing equations, but if you write equation in the Euclidean space, kind of you intersect in general position hypersurfaces, you get rather special manifolds. And just Tom found kind of universal construction how to write equation kind of in order to have more radical topology, and that was further refined in some work by Michael Attia, and then I can relate to that when I will be discussing liposome, how it's in English. Yeah? It has something to do with that, yeah. It has something to do with the structure of our cells, and I don't touch it, but the point of this Tom presentation is that there is kind of key words you pronounce, you say something is generic, right? You have a map, some function on a simple space, so on a sphere with value, I don't care where, and then 0 of that, your manifold given by this equation, but it's manifold only if the map is generic. And generic is a dirty word, yeah? You just say it, it's extremely convenient, but you don't know what you get, right? But this is, on the other hand, the major mechanism of generic manifolds, which is by the genericity. And sometimes you can slightly bypass it. This kind of some interesting situation appears even for hypersurfaces. Say you have a manifold, and you want to look at hypersurfaces, and the way you do it, you take a function and take 0 level, if it is generic. There are cases you can kind of bypass genericity. You have something more effective, and actually this comes from geometry again. If you have a Riemannian manifold, and you can take a cycle and take minimal cycle of minimal volume. And you know in dimension 1 up to dimension 7, this will be non-singular. which is quite a remarkable theorem where the major contribution, 7, come actually from Jim Simons, but there was work Almgren and other people. And in 7 is a strange number, right? And if you go to high dimension, conjecturally, also it seems that this kind of, you may have singularities, but they, on one hand, they kind of spoil, and kind of maybe rather disturbing. On the other hand, and this I will come to this again, the singularities are pretty nice. Yeah, the one which appear in example, they have extra symmetry. So when singularity appear, it may be a nuisance, but on the other hand, it comes with extra structure. And conjecturally, it's always the case. And so and these singularities cannot exist possibly if they're not being special. And there are various conjectures which are only in special cases are proven, how the singularities behave. But in any case, at least up to dimension 7, you can generate manifold without genericity in codimension 1 at least. And what happens for other situations, we don't know. If there is a systematic way to generate manifold with some analysis, whatever, without saying generic. And I think it's logically non-trivial point, yeah. You allow generic or you don't allow generic. For example, if you take like set theory and you don't allow generic, then obviously sort of, yeah, the continuous hypothesis is true, yeah. But if you allow generic, obviously it is not true. Right? It's extremely kind of powerful, kind of logical tool, and we don't quite understand its role in this point. But now, yeah, and another maybe case, well, it's about Markov partitions, but probably I don't have to say much. This actually come from your students, from Schub and from Franks and from Bowen, that you can construct spaces kind of following kind of the Steve horseshoe by writing them by kind of by matrices, by thinking certain kind of by pairs of Markov processes. And it is similar to triangulation, but not quite, yeah, because it may carry extra symmetry to them. But the problem with that, when you have this presentation, it's very hard to tell what topology of the space is, even locally, right? And that's, I think, kind of part we don't understand, yeah? Because effectively, like real numbers, they're given by infinite fractions, by infinite decimals, but then you can say that certain decimals are equal, right? That if we have 999, right, this equal to 1. And these identities are again given by kind of Markov chain. So it's pair of Markov chain. One gives you Cantor set, and another tells you how to glue that. They're called Markov partitions. And this is a very purely combinatorial thing. It's different from triangulations. Every triangulation gives you that, but it's more general in a way, kind of more functorial, but it's rather unexplored. And I'll mention where it leads, yeah, in one way. And now I come to something, my kind of final point. Yeah, so I already was discussing a little bit about singularities and collapse, which two phenomena going together in partial differential equations. And typically, you perceive them as something you want to avoid. Yeah, you lose your a priori estimates, you think become bad. However, typically, when you look closer, and if you're in a good situation, either of the two phenomena, when think either collapse or develop singularity, new structure emerges, and it's beautiful structure, and makes the thing really think much better than you expect. We're very pessimistic and don't like it only because we're not ready to accept this kind of new phenomena. But just in the case of a Perelman, these singularities are coming with extra symmetry, which allows the process. But now, and this is a more kind of interesting part of what I want to say, what are other kind of not so traditional cases to generate manifolds? And when I say manifolds, I mean geometrically significant spaces. Let me start from the end, yeah, because it's Poincaré. So, yes, we speak Poincaré conjecture and that, but Poincaré was another fantastic idea, and which is not what's written in his mathematical manuscript. It was not stated as a conjecture, but just as a fact. And the issue he was discussing in his book, I believe, Science and Hypothesis, was how, from perception we have of the world, we reconstruct the geometric structure of the world. And this is a mathematical issue. And the Poincaré realized it is a mathematical issue, and then was completely forgotten. And the man who brought it up in a different context was Churchill, who was not a mathematician at all, but he has a maybe extremely powerful mathematical mind. He's one of the greatest minds of the century, and we don't know that yet. We're absolutely ignorant of great people if they're not published in a mathematical journal. And he's a genetist, and he's probably the greatest genetist, classical genetist of the century. And I'll tell you what he's done, what problem he solved. Yeah? It was a mathematical problem, but of course, once you realize it's mathematical, how to formulate it, you're kind of done. The point was you could see mathematics behind kind of chaos, and Poincaré was a mathematician, and he was considering kind of easier problem. So what is the problem? So you look at this world. So what's input you receive? Yeah. Very rough, and I mean very simplified approximation, but already quite complicated, is as follows. Oop. So you have your screen, right, where images appear. But it's not physical screen, yeah? There are kind of points there, and then kind of imagine they're numbered in a completely arbitrary way. So eventually you have a string of, 10 to the 4 thing, and all images are given by, according to how they're enumerated. So you have sequence of blacks, right? And you have some number of them, not so many. You look at this world, you have 1 billion of such pictures. And they're not pictures, they're just sequences of numbers, right? 0, 1, 0, 1, 0, 1. Can you say that what you see is hyperbolic space or Euclidean space? Can you? And Poincaré justifiably says you can. But the algorithm, and apparently the only one you can imagine, and I think it has clear-cut idea what we have now, NP complete problem. It's NP complete. It's actually exponential time. If you do any naive algorithm, it takes exponential time. However, we manage. How we do that? Right? And Poincaré indicates the only solution. And solution, he says in slightly different words, and what amazingly, it was very much confirmed by neurophysiology of the recent time. So what you see is not what happens to your, where light comes to inside of your eye. It's a minor issue of your vision. The major issue that you record movement of your eye. That you see by moving your eye, this is what you see. And there is now very good confirmation that this is completely right. For example, when you sleep and your first visual part of your vision is paralyzed, it doesn't move, it's completely dead, you know this by MRI. However, your eye moves. So the muscular system, the part of the brain controlling the move, this creates your dreams, not what you something see there. Yeah? So what you perceive, and this was the idea of Poincaré. And he gave very nice description of that. Yeah? And so this is how you reconstruct. And so the point is, but the mathematical equation which appears here is, so you have this, you make experiments, and something comes out of this. You just have numbers. You have many of these sequences. The question is, what is the geometry behind it? Right? If you knew it came from a screen, but you don't know that. And then this was solved in one instance, and I think it's quite kind of fantastic thing, by Churchill, who was at that time actually 18 years old, and he was a kind of student working in the lab of Morgan. It was another Morgan, it's not you, John. And so what he's done? What he's shown, the genome was linear. That at that time, there were no concepts of DNA of anything. But he said that inside of genome, there is a geometric structure, and the structure is linear. What was the input, right? From where he started. So what they were doing in this lab, they were breeding flies. Yeah? And they're having very particular breeds of fly, and some were kind of with long legs, and some were with short legs, and some were with red eyes, and some were with short eyes. And there were combinations, say, of different kind of quantities. And so you have collections of flies with different distribution of properties. And from that you can derive there is linear structure, right? And it's really absolutely kind of fantastic, right, to think about how we can do it. Yeah. However, indeed, there was the idea of recombination, that certain thing goes along, right? And certain features come together. So you have a correlation matrix. And this correlation matrix, if you think carefully, take its logarithm, whatever, you have a matrix, which it's not exactly like that he was done. Yeah, I'm oversimplifying it for purpose of geometers. But you think about this matrix, or rather logs of this, or x of this, yeah, as a metric. And you look at this metric, and you see the triangle inequality becomes equality. And so it's linear. Right? And of course, it's not like that. He didn't think in terms of metrics, of course, but anyway, he reconstructed he made the first genetic map of X chromosome of this Drosophila. Yeah? So, and now maybe the last what I mentioned, because read this picture and probably you're curious, what your theorem about your paper about Tom spaces has to do with liposomes. So, actually, there are two ways to think about manifolds coming from Archie, if you want to do them in general abstract terms. And one comes from index theorem, and it says that manifold is just a particular cycle in the K theory. And the cycle, so certainly for every vector bundle, you have to assign a number. And the remarkable way to do it, you assign index of certain canonical differential operator twisted with your bundle. And that gives you a number linear function on the space of vector bundles. And you can forget about the rest of the kind of world. And that's a fantastic picture on manifolds, which can go quite far with that. This one way. But there is another way. This is another sophisticated thing. If you don't know that, it looks another look kind of deceptively simple. It's just like almost nothing to say. You say, aha. So what is a manifold? It's embedded into Euclidean space. And then there is this normal bundle. Okay, so it's space and there is a bundle. But so what's special? What makes it a manifold? And the point is that if you think about ambient space as a sphere and you collapse boundary to the point, there is a map from the sphere to the Tom space of this bundle. So it's a bundle with a map to the sphere there. And it tells a tremendous thing because it's coupled with the theorem of Serre, which I was mentioning Serre there, but I was not truly saying much. So maybe I have to return to that because this was a kind of the highest, one of the pinnacles of this kind of soft approach to topology. Because it was soft approach, and then there was some geometric theorem behind it, and still we have no picture of the geometry of that. So the Serre's theorem says that if you consider map from one sphere to another, then almost always you can deform this map so that its dilation becomes bounded. So for every such map, there is another map, which is obtained by homotopy, where dilation, namely by how much curves become longer than they were, will be bounded depending on dimension, except two cases. It's one bad case, and another is this one, when it's not true. Right? If you have usual sphere to the usual sphere, you can turn many, many times around, and just this number of turns, you cannot make it better. In this dimension, that's Hopf maps. Yeah. But otherwise, the theorem says that the homotopy group of spheres are finite, which means you can deform every map to a very simple map. And if you try to deform as a geometry, it's just we don't have no idea what it is. And it's not surprising because there are these numbers. It cannot be a universal argument. So it means some algebra something must cancel. There was some hidden inequality there. But still is kind of one of the central kind of absolutely incredible theorems in topology. And if you apply it to this situation, essentially the theorem of, as I said, there is only kind of finitely many abstractions on the tangent bundle to be, no, normal bundle to be bundled to the manifold. And then it was elaborated by theory of Brauder and Novikov, and saying that that's essentially all that's it. Yeah. There's up to finitely many possibilities, there is nothing else. This representation of a fundamental class of a Tom space by a sphere is all that there is to the smooth structure. And these are your smooth manifolds. So, and now why liposome? Yeah? And these kind of, or liposome, how do you say in English? Liposome or liposome? Huh? Hmm? You don't know? Okay. Liposome, right?
It's lipid, so.
Lipid, yeah, it's lipid, right? So, and these are kind of quite fundamental for us because our cells are made like this, in particular erythrocytes, yeah? And where it's kind of the simplest kind of cells. And they exactly made in the same way. So in this picture of Atia, you think about your manifold not as in this direction, but a kind of as family of these kind of normal bundles. Yeah, it's glued together of these normal directions, and this kind of completely material, this part, but this is important. Yeah, right. So it's space built out of its normal direction, and this is exactly what liposomes are. They are built of these molecules. Yeah, there are lipid or bilipid molecules. And these things just may flow in solution, the way they want, and this will be just a mixture of them. But if you start cooling them, they conglomerate and form particular surfaces, yeah? But surfaces built out of them, yeah? And that's fantastically complicated process. It's complicated in this detail, but it's complicated because we have no idea what kind of mathematics behind it, yeah? There are kind of even the most elementary questions we cannot answer. So just one thing, of course, when you come to this kind of low temperature limit, we have the surfaces, this first-order differential equation, the variational equations, already these equations out of our scope. Yeah, we don't know the most elementary question, which biologists believe they know the answer, but we don't. You know, our erythrocyte is like that. Yeah. And it is spherically, circularly symmetric. And the model which you have for erythrocyte is built out of these things, and they stick together, and they're completely flexible in this direction. Yeah, you know, there is no friction in the molecular world, but they don't want to bend. Therefore, there is bending energy, which is essentially squared curvature, integral squared curvature of that. So erythrocyte per given area and volume it bounds has minimal bending energy. Assume it. Why solution is symmetric? Yeah. If it's symmetric, you know it has a shape. Yeah, that's this apparently what this biologists, whoever, they can write down the equation. But why it is symmetric? There, of course, my understanding, they take it for granted. It must be symmetric. But why it's symmetric? Well, it's unknown. And this is a kind of little beginning of a apparently very big subject, which we don't understand at all. And for me, the most remarkable point, there are many equations, but what's I think most remarkable, abstractly, mathematically, which we don't understand, when we heat it up, they all disappear. However, they all come with the same Gibbs ensemble. There is just one parameter. And therefore, all our differential equations, all Bochner formulas, identities, here, they cannot die. Yeah? They're analytically continuous, but continuous to what? Right? So there is something in this ensemble of these particles, when they hit it, which already knows they come back and become this particular surface. And this instance, the simplest instance of this equation. And actually, something like that mentioned in the work by Perelman. Yeah? In the first lines of his article, he speaks about entropy, and he gives kind of geometric interpretation of, of some version of the energy function for Ricci flow, and explain it's kind of similar to Gibbs ensemble. Right? I don't understand what's written there in English. I know the words, I never penetrated that. This picture is more picturesque because in concrete space, and that's an abstract kind of equation. But this abstract equation also may have this interpretation. It's kind of converged through something much more flexible, but still remembering basic symmetries and basic equations. And that, I think, is that's fun to pursue. Yeah. Okay.
So any questions or comments?
Yeah?
No, nothing. But in this last thing, is there some energy? Could it be due to some stability criteria?
No, well, in the end, I mean, it takes a variational problem. But the question is, what happens to this equation of this variational problem when temperature goes up? It's kind of, it's just, you know, in the Gibbs ensemble, it's a very simple function. You look at one particular value, class of values at this point. If you look at the kind of try to imagine perturbation theory for that, yeah. So you look at the expansion, you immediately run out of nothing like differential equation. You immediately see things completely discontinuous. You just try to be close to physical model. It will be perturbation. Mathematically, will be boop, you know. I know nothing. I think nobody knows anything. Yeah. Just all differential equations become kind of babies. Yeah, compared to this problem. But this, on the other hand, is kind of we live in this. Yeah, we would be dead without that instantaneously. And it's some kind of mathematics physicists say, well, just low limit, and they don't concern. But I know some other examples besides. So first, it fits. I think not quite superficial with this picture of manifolds. Yeah, it fits with this picture. I know some other mathematical instance of that when the same picture emerges, also in topology. But in statistical mechanics, nobody looked at this from this angle. So the point is, what if you take a beautiful mathematical equation like that, or Perelman, or whatever, and think about this as a limit of some statistical thing, decompose it into infinitesimal elements, but in a more intelligent way, and break these elements, but keep something, so they will know how to come back. Can you do that? Like for Hodge equation, for any equation. This is essentially a minimal surface equation. You can do that. But nature does this. We don't know how to do that. If you look at what goes, actually, it's not so simple. It's not that the particles stick together. There is no sticking energy between them, not at all. Yeah, it's much more subtle. Why they come together? Why they come together? It's entropic phenomenon. It's not energy. We see it as an energy, but it's entropic. So it's not something we know. You don't know this. I believe, well, maybe some people who do experiments probably know something. But theoreticians, well, I doubt. At least I tried to ask some people. Nobody has any idea of that.
So, yeah.
Sorry, for the a question about the asymptotics. Is the a to the k asymptotics not known even for the case of three-sphere manifold?
Yeah, for three-sphere it's unknown.
It's unknown?
It's unknown, yeah. It's made now in view of the Perelman and the development of hyperbolic manifolds. It's possible it will be exponential. Possible, yeah. But it's certainly unknown. It's very well beyond what can be done.
But, for instance, isn't there two spheres that one can find directly in the triangulation, which an equatorial like?
No, so okay. So what? You find it, so what?
Okay, well.
It's absolute. No, the question is you may have very strange turns in this triangulation. Okay, you cannot have the hidden Turing machine, that's for sure, which it may be relevant for that, but it's not clear why the two things are relevant. Well, there are this question about the asymptotic. The whole literature in physics that is about that, and there are many versions of this question. You can formulate in very elementary combinatorial terms about graphs or about matrices, and there's many reformulations, but they all look extremely difficult because we have object built out of local data, and then you have this global invariance, even very simple, and then you realize this link is kind of philosophical. Yeah, when you make some step, yes, you kind of logically you make it, but when you look at this, you see nothing. And this instance, it shows you how poorly you understand it. Yeah. It's a very clear-cut problem and a measure of our ignorance.
Thank you.
Okay, more questions? So if not, then thank you.